today, I really want to sort of give the overarching talk of how the accelerating universe, at least from my perspective, developed, the basic assumptions we make in this, how it sort of happened, and what's going on right now. And I'm going to try to do that in a reasonable amount of time. So I think we always have to remember that when we do cosmology, it is built up on a house of cards that we hope is correct. And that house of cards really comes down to the fundamental assumptions we make, which are based on the theory of general relativity, and this single assumption that the universe is homogeneous and isotropic on large scales. Now, we can test these things, but the fundamental results that we're presenting today rely on these two things being true. So let's just remind ourselves, since I realize all of us don't do cosmology at a time, of the standard model. So the standard model has a few ingredients. The isotropy is geometrically described by what we call the Robertson-Walker line element, which connects distance between 2 points that are separated in time and by some coordinates. But we have to worry about a couple things because geometry is complicated in curved space that happens to be expanding or contracting. So we have to worry about the curvature, and we have to worry also about the dynamics of the universe, the scale factor. And the scale factor is related to the observable that we use as astronomers, redshift, how much an object's light is shifted to the red, and that sort of tells you how the scale factor is changing over time. So just graphically, so we can get an idea, when we want to look at 2 points, we have to worry about whether or not it's a scenario like this, where you have a universe expanding its curved space, or perhaps a universe that has curved with a different shape, or possibly even flat. And so the Robertson-Walker line element really keeps that straight. That does that bookkeeping for us. The other thing we have to worry about is the dynamics. The dynamics is where general relativity enters. So we have to worry about how A of t, the scale factor, changes over time. And so Einstein in 1915, 4 days after Hilbert, published his equations of general relativity. Now, Hilbert, of course, used all of Einstein's work to sort of do the math at the very end, but Einstein's equations are, of course, a very complex network of nonlinear differential equations. And when you go through and take isotropy and homogeneity, then you can break those down into very simple equations, which people like myself can actually solve because they're ordinary differential equations. For example, here the Friedmann equation for a flat universe, which is a very simple differential equation. Here we have the scale factor changing as the Hubble constant now, so that is the rate the scale factor is changing now relative to the scale factor. And then we have to worry about a couple things. So, for example, how density is changing versus scale factor changing. And so the Friedmann equation is what allows us to see the dynamics of the universe. Finally, we have to worry about what is in the universe, because not everything's density and scale factor changes the same, and that's the equation of state. So the equation of state really tells you how the density of material changes as the universe expands. So for example, normal matter, atoms, dark matter, stuff that we call pressureless in general relativity, its density goes inversely as the volume, or you can think as the density scaling as the scale factor cubed. Well, that's fine if you have atoms, but we also have things like photons. Now, a photon, if it's in a piece of the universe, it expands with the universe and it gets longer in wavelength. And so its scale factor, it has a different density, different equation of state as the universe expands. So in this case, the density scales is the scale factor to the 4th power. You can imagine something like the cosmological constant, which is constant. And so in this case, it doesn't scale at all with the scale factor. The density is constant over time. And this is important, and you don't have to look at this, I just want to show you how easy it is to do, is that if you have a flat universe made out of normal matter, you can solve the Friedmann equation by substituting in how density changes, and you get that the scale factor evolves as t to the 2/3. If I have a universe full of photons, and I do that same differential equation, the universe expands as t to the 1/2. And as a cosmological constant, again, same substitution, exponential expansion. So what is in the universe affects the dynamics of the universe. All right, finally we have to think about if you have stuff in the universe, the balance of the universe is going to change. And that's because the amount of the energy density of photons, for example, goes up as the redshift to the 4th power, where the density of atoms goes up as the redshift to the cubic power. So if there are photons in the universe, we know them from the cosmic microwave background, atoms in the universe, the people in this room, we know that that ratio is going to change, such that in the past, at some point, if there are photons in the universe now, then they will eventually dominate. Cosmological constant, same idea. It's constant in time. The density of normal matter will go up as the redshift cubed. And so at some point in the past, if, for example, the cosmological constant is dominating now, it will not dominate in the past. So you put this all together and you essentially get what we call the standard model for cosmology today. We know that we have a cosmological constant or something like it. We know we have matter, we know we have radiation, and so this sort of tells you have a history of the universe which is sort of, as far as we know right now, in at least 3 pieces. So let's now move to observationally testing this model. So I'm going to go back to some history and say 1994, I just finished graduate school, and I would say that the predominant view in the world of cosmology was that the universe was made up of normal matter, stuff with an equation of state of W equals 0, stuff that behaves like atoms, although it may have been dark matter as well. And so we segregated into 2 groups, theorists who believed very strongly in the inflation paradigm and cold dark matter. And this paradigm, which I'm not going to talk too much about today because I know most of you have at least heard of it, predicts that the total omega of the universe, or the curvature of the universe, should be 0, omega should be 1. Now there are ways to get around that, but they're, I would say, not very nice, and so it's a very generic prediction that omega would be 1. Now we knew that the universe was about 13 billion years old in 1994, give or take a few billion years, and in order to make a universe that has omega equal 1 in normal matter, it turns out, because it expands as t to the 2/3, that the age of the universe by the Hubble constant is 2/3 of that value. And so you really needed a Hubble constant below 50 kilometers per second per megaparsec. And the way they accounted for this is that the observers who had measured that omega matter was roughly 0.2, and the Hubble constant was greater than 50, I would say most people would have said it was 60 to 80, were simply wrong on those measurements. And so we sort of segregated these 2 questions. Theorists who believed in this and said, these measurements are not correct right now, and the observers who said, well, we made this and we just don't think inflation and cold dark matter are potentially right. So that was sort of where we started in 1994. So if we look before that, that really came about from the 70s and 80s with inflation showing the uniformity of the cosmic microwave background and providing the seeds of structure formation and a few other things. Cold dark matter came out of the idea of initially having some non-luminous form of normal matter, but it also had the advantage of really showing structure formation that matched the observations. And these things predicted the flatness and how structure grows on different scales. But by 1990, there were some problems. The first measurements of large-scale structure were made, and it was realized that an omega matter equal 1 universe with a reasonable Hubble constant, provided it really didn't match the large-scale structure. There was too much structure on large scales compared to the observations. And so there were problems. People were scared that maybe this idea of CDM was dead. George Estafio and colleagues showed that they could fix this with a cosmological constant at the time. And, but why didn't they persist? Well, if you go back and look at subsequent papers, they ultimately just thought that the cosmological constant was a bridge too far. There were reasons why you might think that the cosmological constant should be much, much bigger, from particle physics ideas of virtual particles filling the universe. And so the way to get rid of that is essentially making it go to 0 through some unknown process. So the idea back in 1990 of having a cosmological constant, I think, was just too foreign to be accepted, even by people who had written on the subject of it, potentially fixing various observations. But that wasn't the only way to fix things. You could also fix it by making a Hubble constant very, very low. And you will notice at least a couple people in this room, or who at least frequent this room, writing this paper in 1994 saying, we can fix a lot of problems if only we have the Hubble constant be 30 kilometers per second per megaparsec. And that's a very old universe. That would be a universe that would be probably 18 billion years old, even with the deceleration. And so Joe Silk, who was someone I had come across several times during my graduate studies, was visiting Mount Stromlo that time, and we decided we would have a wager with him on the value of the Hubble constant, since he was willing to publish that it was 30 kilometers per second per megaparsec. So we bet him that it would be greater than 60, and that would be figured out by the beginning of the millennium, the 1st of January 2001. So we felt pretty good about this, but we made one crucial mistake, which is that we had Jim Peebles adjudicate, because Jim Peebles is also a theorist. I don't know what we were thinking. But anyway, we went out and we pressed in the end of 2000. So for example, here is a meeting of people, and you will notice a couple people in here, a very young Mr. Mamon here, voting that the Hubble constant was less than 60 in 2000. So I can understand why you guys are at the same institution. But we had about 2 standard deviations. 95% of the people agreed the Hubble constant really was greater than 60. And the sad part for me is I even have Joe Silk here giving a talk at the end of 2000 saying the Hubble constant was 65. So I presented this evidence to Jim Peebles, and he said, no, it's not 4 standard deviations, so there's no decision on this bet. So there was no outcome on that bet, unfortunately. But I think we all agree now that the Hubble constant is some number slightly greater than 70, give or take 5% or so. There were other people who were looking at the current state, and the idea of the cosmological constant fixing things reared its head several times, but there was a common theme. They were written by theorists with the assertion that inflation and cold dark matter are correct. And maybe the most interesting one was this one by Ostreicher and Steinhardt, who actually tried to constrain flatness through the first observations of the cosmic microwave background. Now, this data looks very, very convincing. I think the problem is that this curve is maybe not exactly what a modern curve would look like through those data points that was an omega equal 1 universe. Nonetheless, again, was with the idea that inflation or something like it must be correct. Should also say in 1994, 1995, the omega matter observationally, most people thought it was about 0.2 or 0.3, but it was not clear. There had been work looking at the motions of galaxies through something called the potent algorithm, where they tried to reconstruct mass versus the motions, and they suggested things like omega matter were 1. Joe Moore had gone through and modeled clusters, and also showed that things like an omega equal 1 universe fit those data at the time of clusters better than non-models. And so it was a bit of a mess, and it was a good time to do a new experiment. Now, the experiment that we wanted to use was to use one of the fundamental observables of cosmology we call the luminosity distance. And these were really written down for the first, well, I would say comprehensively written down the first time by Alan Sandage in 1961. And the idea that you measure how bright an object is as a function of redshift, the luminosity distance. And you can write that down with our standard model as an equation. That's a little messy, but in the end, if you look at it in detail, besides having to just calculate it, it is quite simple. The brightness of an object depends exclusively on what is in the universe, how much, and its equation of state. So let's look at this equation. Inside this integral, we have all the different species of matter and how much there is relative to the critical density and their equation of state. We also have to worry about curvature, but remembering that curvature is just the sum of all of the densities of matter relative to the critical density minus 1. And then we have the Hubble constant out front, and that's just an overall scaling thing. So we don't actually need to know the Hubble constant to make a measurement on, for example, the omegas in the equations of state. It's just an overall normalizing constant. It tells us how old the universe is, but it isn't required to do these parts. So if you graph those curves out, you see something, and I'm going to look at it here, where I take the curves of distance modulus, so logarithmic distance, versus logarithmic redshift, and I'm going to subtract off an empty universe, and we're going to look at this. And so in 1994, when we started out, we were expecting to weigh the universe. How much omega matter was there? Was omega matter equal 1 right, or was omega matter equal 0.2 right? And that was a very simple measurement. You essentially compare this curve versus that curve, and you can see where we were working at a redshift of 0.5, the difference was about 0.2 magnitudes. That's about 20% in flux difference. And so not insurmountable, but not an easy measurement, as astronomers are likely to make mistakes of factors of 2 sometimes. And doing a 20% measurement, of course, was going to be challenging. So the way we were able to do that was with something called type 1a supernovae. Now, I'm not going to talk too much about type 1a supernovae themselves, except for to say that they were the prodigal son of cosmology, this idea of something that had been around since the time of Zwicky in the 1930s as a way to measure relative distances by looking at how bright these things were. They had developed a reputation of being all identical. The reputation was based on interesting data, though. Fritz Zwicky was responsible for most of it. In the 1930s, he imported the Schmidt telescope concept and some of the optics from Germany, from someone unrelated to me, as far as I know. And that 18-inch Schmidt telescope, you could put a photographic plate in, and you could scan large hunks of the sky at a time. And then by blinking, looking at one plate and another plate taken a month later, they had these stereoscopes where you would sort of block out one side and then block out the other, and your brain sort of found the new objects. It was very effective. The human brain was a good computer back in the 30s. By 1968, Charlie Cowell, who just passed away in November, plotted the brightness of the type 1 supernovae. These are objects that did not have hydrogen in their spectra. He plotted how bright they were versus their redshift. And he got the first type 1a supernova Hubble diagram. He noted that these objects were not all observed at maximum light, and the quality of photographic photometry is very poor relative to what we are used to today with CCDs. And so the 30% scatter in this diagram was consistent with the type 1 supernovae all being identical, and hence that is where the reputation started. Unfortunately, because digital detectors did not really become widely available until the end of the 1980s, the data did not get much better over this time. That did not deter a group in Denmark going out and looking for these things with the first small format CCDs. In 1988, after 2 years of work, they discovered an object at a redshift of 0.3, but it was well after maximum, and they had spent 2 years to find one object. They knew they needed about 20 of them, and so they gave up, saying, this is just too hard right now. At the same time, a group in Chile, spurred on by Alan Sandage, went through and decided to go out and really test type 1a supernovae. And so the idea was to go through and to use the same technique that Zwicky had used in the 30s, because in 1989, the largest CCDs that were available were about 1,000 pixels on a side. And although they were 50 times more efficient than the photographic plates, they were many thousands of times smaller in scale, and it just was not possible to easily go out and do these supernova searches digitally at the time. And so here's one of these blinking machines where you put the plate in plate and then look here and it switches back and forth. Jose Maza with one of these plates. And I had visited Mario Amui and Nick Sunsef and Mark Phillips and Jose in 1991 as part of my thesis. And I had met Mario here in France as part of a Les Ouches school in 1990, and he had told me he was starting this program, and I said, okay, it sounds good. So I visited him in 1991, and Mario was very depressed. He's like, type 1a supernovae, they're not all the same. And he showed me this light curve, supernova 1990 AF, and he showed me that this object fell a bit quicker than the average, and this object was fainter. That is, it was out a long ways out in the Hubble flow. It was at a redshift of about 0.03. And he had other objects at 0.03 as well, and this one was 50 or 60% fainter. And they had done something different. They were using those small format CCDs to follow up digitally and getting really precise light curves of the objects that they had discovered photographically. So instead of being stuck with 20% photometry from photographic plates, they were getting 1 or 2% photometry with their CCDs. So that was a huge change. In the end, it was realized pretty soon after by Mark Phillips, who had the benefit of the whole Colon-Tololo sample to look at to really see what was going on, I think, that how fast a supernova fades is related to its intrinsic brightness. Things that rise and fall quickly are faint. Things that rise and fall slowly are bright. We now understand that is because type 1a supernovae are powered by the creation of nickel-56, which then decays to cobalt-56, which then decays to iron-56, releasing gamma rays in each one of those transitions. And that iron also has a lot of opacity. And so when you take the nickel decay, lots of nickel means you have lots of opacity but lots of energy. And lots of opacity means the diffusion time is longer. So they have broader light curves, but there's more energy, so they're brighter. And so the detailed calculations of these, I would say, are probably consistent with this picture at the 5 to 10% level. Unfortunately, it's not good enough to actually use theory alone to predict how bright these things are. They're just, our models are not as that good. But the basic scenario is understood. So in 1994, Mario, again, I had finished my PhD now. He came up in 1994, and they had their first set of objects. And he showed us this diagram. And he said, once we correct for Mark Phillips objects, from a separate sample of data, it turned out. So this really was no extra degrees of freedom of fitting things. It was using one set of supernovae to correct another set. This was his Hubble diagram. A scatter of 12% in flux. That's 6% in distance. Now, I've already told you the cosmological models are separating out by twice that. So each object here would be giving you a 2 standard deviation measurement of the cosmological model. So these things were great. I was really excited. These things are suddenly, I realized, were precision distance indicators. Eventually, this group had 29 type 1a supernovae out in the Hubble flow, and these have provided the fundamental basis of using type 1a supernovae as accurate distance indicators and used by both teams in their measurements of the acceleration. They're the low redshift anchor. The other thing that happened in 1994, about a month later, is we had access to the multiple mirror telescope, which is a 4.5 meter telescope, much maligned, but actually a very good telescope. It, as a spectroscopic machine, was really good. It was the most powerful spectroscopic telescope in the world. I've compared data with the 5 meter, and we got better data with the MMT than the 5 meter took at Palomar by quite a bit. So Saul Perlmutter, in 1988, was part of a team that was essentially trying to do the same thing as the Danes were, which is to find supernovae. Now, the group that I was part of, we studied supernovae, were concerned that supernovae had not been shown yet that you could measure distances with them. But they felt this was so important that it was important to go out and look for these things. But in 1988, the technology was hard. By 1994, large format CCDs, 2,000 by 2,000 pixels, were now available. And that allowed us to look at, on a 4 meter class telescope, patches of a sky roughly 15 arc minutes on a side. So that was big enough to actually find supernovae, it turns out. And Saul Perlmutter's group did this. They emailed us. They had done this on many, many occasions to follow up what they said was a candidate. We had taken data unsuccessfully for them in the past. But this time, I was at Harvard And Bob Kirshner, Adam Rees, and Pete Chalice were out at the MIT, and they faxed me this spectrum, which they said, doesn't this look like a type 1a supernova at a redshift of 0.42? So I checked it out and I said, yes, it does. Amazing. What is this? So it turns out it was Sol's candidate. So after a while, it turned out we found out they had discovered 7 objects in the previous 3 months. And that was because the technology had suddenly got to the point where we could scan enough sky to find these things. So that was the other key ingredient that happened. Now, it became pretty clear after a few months of working with Sol that the way we as astronomers studying supernovae were going to approach the problem was very different than the way Sol, from his particle physics side, was approaching it. And I would say that it was clear we weren't going to easily be able to work together on a problem. I was, of course, a young 27-year-old looking for something to do after my PhD, and I was visiting Nick Sunsef down in Chile. Here's Nick Sunsef. And we discussed the idea of saying, well, you guys have this new technology of how to measure supernovae distances accurately. Sol clearly has shown you can find them. The CTIO4 meter has a brand new 2K by 2K CCD on it. Let's start our own program. And we were born then. We brought on the whole team. We needed, obviously, a fair bit of telescope time to find things, and that's how we were born. So in September 29th, 2 days before my first son was born, this was submitted literally while my wife was in labor, fortunately by colleagues, our program was born. And the idea was we would go out and measure Q naught, which is the deceleration parameter. So in the normal model, Q naught, the deceleration parameter, which is the second derivative of the, essentially the scale factor, that has a value between 0 for an empty universe and a half for a universe which has omega matter equal 1. So we were going to go out and measure that, and we figured with 30 type 1a supernovae we would really, really be able to nail, actually with 20 in this case. So the hard part was I was arrogant, and my view at the time was, well, if Sol Perlmutter and those guys can find them, we sure can find them. No problem. But in 1995, 2,000 by 2,000 pixel images were really big compared to the computing power of the day, where we would end up taking one of these nights tens of gigabytes of data, but our hard drives were only a gigabyte big. And so we had data scattered across the observatory on computers that turned out to each single one had a different version of an operating system, so that when you ran on a new machine, you got an LDS01 error, and oh God. So I spent a lot of my time doing computer science rather than actual science. But the hard part was finding these things. And so here's an image, 5,000 galaxies, and the goal is to find the object. And I knew more or less what Sol had done, so we could, at least in practice, I had the basic idea. You take an image, and you don't take one image, you take 2 images. And essentially what you need to do is you need to line them up and then convolve the first image to match the second, scale them up, and subtract. This turned out to be quite a challenging thing to do in 1995. There was not software like Allard and Lupton's at the time, so you sort of had to homebrew it all. And so we had something that sort of worked. I made the, I would say, rather crazy mistake of when I first moved to Australia of saying, I have 50,000 lines of code. It works fine on test data. I'm going to stay in Australia while this is running in Chile. And that turned out to be a mistake because it, of course, did not run very well, especially since we didn't even know what version of operating system we were using there. So in the end, we spent a lot of time, whether you were a graduate student like Saurabh Jha was at the time, a postdoc like Peter Garnovich was at the time, or a full professor like John Tonry was, looking at data, checking how well the things that Brian's software put out. So it was really a huge team effort that involved no sleep for several weeks at a time, I'm afraid. So to give you an idea, I'm going to give you a quick movie. Since many of you haven't been to Chile, some of you probably have, here's the CTIO4 meter. And as dusk falls, we would look out at the other team. Here's Greg Aldering, because, of course, they were using the telescopes that we were using at the same time. So we'd share the telescopes with them. And we would go out, and as the night went by, we would have people up at the telescope. For example, Nick and Bob Schomer, who has unfortunately passed away, up there, making sure that we pointed exactly to the same fields that we did a month ago, because if you observe a new one, it doesn't going to do you any good. Checking the data, making sure everything was okay. And then down off the mountain, we would get the data there, and we had essentially a sweatshop with people looking at the candidates saying, is that a good one? Is that a good one? Is that a good one? And there was a very good time horizon, because of course we have to get spectra of these. And the spectra were going to be taken at the other side of the world, at Keck, the largest telescopes at the in the world still today. And so there we had to quickly get candidates out for people, for example, Alex and Adam, to take spectra of these things so that we knew what their redshifts were and what they were. And of course, we were sharing the telescopes again with Sol on that end. So we really used the same set of facilities. So in 1995, after our 6th night, I had absolutely no candidates of supernovae, and because we just could not get the software to work. And we had to develop all sorts of little tricks, because it turned out the internet connection speed between Australia and Chile in 1995 was 1 character per second. L, S, return. Oh no! There's 1,000 files in that directory. That's going to take a half hour. So it was tricky. So in the end, I ended up not logging on at all to Chile, and I used a phone where I would call them up, and I would say, I have just emailed you 15 lines of code, so that'll take about a half hour to get there. And when you get there, I need you to insert it at line 73, and then run it and tell me what happens. And so at the end, I really thought the end of my career was nigh, because it was clear we weren't going to find anything. And then suddenly things started okay working. And I remember that our stamp, we had different fields, and field C, stamp 14, C14 came. And this is what was sent to me. It probably took about a half hour to get to me. And here was an image taken in February 1995. Here was the data taken in March 1995. This is the convolved, this observation convolved and matched to this observation. And this is the subtraction. This is really the thing I did when we first found this. So I've got typos in this and everything. And so that was supernova 1995K, which we didn't have access to Keck, so we had to use a 4-meter telescope to get a spectrum. So that was all night on an ESO telescope, the NTT, 8 hours. And we found out it was a redshift of 0.48, so it was the most distant object at the time, and our bacon was saved. We were able to march again and get more telescope time. On September 30th, 1995, so a year after we started, we already had that object, and this is the actual proposal. Supernova 1995K, one of our best observed objects, was our first one. We got really good data on it, but it was in this funny part of the diagram. It was quite faint, but it was one object. It had uncertainties associated with it. We didn't worry too much about it. Unfortunately, the Kit Peak TAC did. And they said, so we got 2 proposals, one from Sol's group, one from yours. Sol's getting omega matter equal 1. Here you are getting negative Q naught. You guys obviously don't know what you're doing. We're going to give the time to Sol. So that really happened to us in September 1995. And I said, what do you mean negative Q? I said, look at the error bars on that. Come on, guys. So I didn't think we had measured anything about negative acceleration at that point. I just thought we had one object. Anyway, so people often ask, well, when was the Eureka Moment? There was no Eureka Moment, at least not for me. Adam Rees, one of the benefits of being a 27-year-old running a team is I get to call the shots at some level, and my shot was, there's a bunch of us people who do not have jobs who are going to do all the work, so I think we should be the ones who get to write the papers. And that was agreed by our group as being a perfectly reasonable thing to do. And I think at the time it seemed reasonable to me. I just realized how lucky I was for that to be a reasonable thing to do. And so at that time, Adam was writing up this, our third paper. I wrote the first one, Peter Gardnovich the second, and Adam the third. And Adam was great because he was focused and he worked incredibly hard, nothing but this, getting this done. Because we knew we were well behind Sol's team, and Adam more or less caught us up in a period of about 6 months. And so he sent me a Hubble diagram. as a figure and said, what do you think? Question mark. And I looked at it, clearly showed acceleration. And I wrote back and said, all right, what have we done wrong? Here's his lab book where he had done the calculation and found negative omega matter if you assume cosmological constant was 0. So I didn't go through and suddenly start fitting cosmological constant models. I started redoing photometry, redoing K corrections, redoing Moltke's bias corrections, redoing photometric sequences. We did everything over again. And so after about 6 weeks, on the 8th of January, 1998, Adam and I agreed to 3 decimal places on the whole calculation. And I said, hello, Lambda, in an email to him. And at that point, we decided we had better tell the team. So we told the team, and the team was interested, but just to give you an idea of what was going on, it turns out Alex Filippenko, Adam was at this point at Berkeley, and Alex Filippenko knew about Adam's result from earlier on. And Alex is very enthusiastic. Adam showed me a fantastic plots before he left for his wedding. So we started when my first son was born. This all happened during Adam's wedding. So Adam told the team and went and got married the next day. And so our data imply a non-zero cosmological constant. Who knows? This might be the right answer. Bruno Leibengut here in Europe, concerning cosmological constant, I'd like to ask Adam or anyone else in the group if they feel prepared enough to defend the answer. There is no point in writing an article if we are not sure we're getting the right answer. I myself in Australia, who had been in this, and there's a whole big long article on this, basically said, I agree our data imply a cosmological constant. I had gone through. But I was worried. How confident are we in this result? I was worried about systematic errors. I find it very perplexing. It was a crazy result to believe in. Bob Kirshner, I am worried. He was Adam and my PhD supervisor. In your heart, you know the cosmological constant is wrong. Though your head tells you you don't care and you are just reporting the observations. It would be silly to say we must have a non-zero cosmological constant only to retract it next year. Mark Phillips in Chile says, as a serious and responsible scientist, we all know that is far too early from reaching firm conclusions about the value of the cosmological constant. John Tonry in Hawaii, who remembers the detection of the magnetic monopole and other gas? On the other hand, we should not be shy about getting our results out. Alex Filippenko, who was at the same institution as Saul Perlmutter and really did not want to be scooped by Saul. If we are wrong in the end, then so be it. At least we ran in the race. Adam Rees, now back from his wedding, ready to go on to honeymoon. The results are very surprising, shocking even. I've avoided telling anyone about them because I wanted to do some cross-checks. I have, and I wanted to get further into writing up the results up. The data require a non-zero cosmological constant. Approach these results with your heart, not with your heart or your head, but with your eyes. We are observers after all. And then Alejandro Clocchiati down in Chile did my favorite quote, if Einstein made a mistake with the cosmological constant, why couldn't we? Okay. And Nick Sunsef, who was really one of the mentors of this, Nick Sunsef started the program with me, and he sort of acted as my mentor in leading this group, said, I really encourage you, Adam, to work your butt off on this. We need to be careful. If you are sure that the cosmological constant is non-zero, my God, get it out. I mean this seriously. You probably will never have another scientific result that is more exciting come your way in your lifetime. And that he was certainly true on. All right, so what did the data look like? At the time, our data are plotted here in a Hubble diagram. I'm going to look down at this one. And you can see our data in black and Saul Perlmutter's group, who got the same result at the same time. So should say that at the same time, our groups were not terribly friendly, as many of you will have observed across the era. I always got along with them fine, but other people maybe not so well. So we didn't really know what each other were doing. On the 1st of January, 1998, I was in Australia. I thought Saul was still getting omega matter equal 1. And here we are with this crazy accelerating universe, and I was perplexed. By the 10th of January, it became clear to me that Saul's data had changed a fair bit, and the cosmological constant was consistent with his data as well. At the same time, they didn't know we had this data, so they were mulling over the cosmological constant, and this all came out in early 1998. So the two groups, which had not agreed on anything particularly in public before, suddenly agreed on a crazy result. The universe seemed to be accelerating. And so they had more points than we did. but our points had better data per point, and we had 2 colors for each point. So in the end, the statistical significance of each result was almost identical, which I'll show you in a probability density function between omega lambda and omega matter. You can see we get almost the same answer, and our error bars are almost identical. Now, you could notice that it's only, if you go through and integrate this and compare, well, do we need to have a cosmological constant or don't we? It's about a 3 standard deviation measurement for each group. Now, many of my colleagues now are particle physicists, and they say, well, we don't do anything at 3 standard deviations. But I would say on our defense that if you take our 2 data sets and put them together, it was very close to 5 standard deviations measurement. And so we had an interesting measurement, but of course we had used the same technique, type 1a supernovae. So the group, of course, wrote this paper, and here we are in Stockholm with our all dressed up. We had the entire team there. The only time we have all been together at one time, the Nobel Prize ceremony. So, and the other team was there, and I don't have their picture from the Nobel Prize, and they had almost everyone, all but a couple people from their team were there. So these two papers were submitted in 1998, and as I said, pretty much came up with the same answer. So our high Z observations, were incompatible with any matter-only universes at some reasonable significance. But the supernovae themselves might be affected by things that we in common, evolution, dust. And so I think a lot of people were reasonably justified in saying, okay, we need to see more. I should also say that at the time, though, this, of course, as shown by various theorists, fixed a lot of the problems in the existing model. The only thing it was really uncompatible with were those few high omega matter measurements, which were controversial. And this one measurement done by Chris Kachanik on lensing limits, which I think has now been discarded for reasons I'm not completely sure about, but I never hear about it anymore. But it was pretty much compatible with everything. It was just a big addition to the universe to add 75% of the universe of stuff that has negative pressure. That's a pretty big addition to the universe. We were already working on the idea of the equation of state back in 1998. We didn't know about the idea of calling it W. We called it alpha. And for a flat universe, we could show that really, for a reasonable value of omega matter, it needed to be something like a cosmological constant already in 1998. Now, the thing that really transformed my level of certainty from saying, I'd bet my goldfish, to I'd bet my dog, was the cosmic microwave background. In 1998, here are the state of the measurements and showed you an high omega matter and a low omega matter universe. And there was one point, if you believe that one point absolutely, then you could begin to say the universe was flat. But that wasn't really enough to convince me because it didn't even show that the theory was right. But then in 2000, Boomerang and Maxima came out and really showed that first Doppler peak, what its scale was. And so here we were able to compare the physics of sound waves in the early universe, their scale, which is known to very, very high accuracy from the physics, cosmic microwave background, and compare that to how big the angular scale on the sky. And that resoundingly showed that the universe was very nearly flat. And once a flat universe was measured, the supernova measurements went from being individually 3, 3.5 sigma at this point, to much, much greater than 7 standard deviations. And so at that point, I said, okay, I think we're onto something here. This really does something, nothing seems to be, it all is consistent. Progress happened quite quickly. 2DF redshift survey found essentially the power spectrum, and then by looking at infall around galaxies, we're able to measure omega matter quite convincingly at being 0.3 thereabouts. And you could combine that with the supernova and the CMB and get new constraints. And in the end, by 2003, when we had the WMAP show really the whole curve was consistent, we had a situation of 3 experiments that overlapped in this very specific part of the diagram, omega 0.3, cosmological constant 0.7. And the only way for the result to go away was for 2 of the experiments to have very large systematic errors. So more recently, we've seen work and come up from the idea of these acoustic oscillations in the cosmic microwave background, imprinting galaxy structure with that scale, with that acoustic scale. And so that acoustic scale is known very well from the physics of the CMB, and now it's a matter of just seeing that as a function of redshift. The difficulty is if you want to measure that scale, and here it was, I think, first convincingly measured at about 2.5 standard deviations is all, though, in the Sloan Digital Sky Survey luminous red galaxy data set by Eisenstein, we had the scale here, which we could compare at a redshift of 0.35 to the CMB scale. And so that allowed us a new lever arm. And so it is possible to make these nice measurements. Now, the baryon acoustic oscillations have two great things. First of all, it's a physical scale we understand from physics alone. And the other thing is we're comparing an angular distance where if dust is there, evolution is there, we don't care. We can measure angular distances to 1 part in 10 to the 7 very accurately. And so it's philosophically a very clean measurement. Of course, there may be some wiggling around of the baryons and things, so you've got to worry a bit about that. But philosophically, it's a very clean measurement. The hard part is you need about 100,000 test particles and a volume of about a gigacubic parsec to do it. And those are a huge experiment, which I would describe as mind-numbingly boring, really, because you just really go through and take a redshift in a direction and do it and do it and do it. And you add them all up, and that very simplicity of it is what makes the method so strong. It's almost impossible for it to go wrong. And so at this point, this method has really come into its own in the last year. And if we go through, and I'll show you the latest results, but I'll also show you that the people here, especially people here at Paris the 6th, as part of the Supernova Legacy Survey, have filled in with very, very nice data. The Sloan guys have done very nice data at moderate redshift. And of course, we have more and more data at low redshift. And so the supernovae, instead of just being a handful of objects, are now on order of 1,000 objects. And if you take the best fitting model, which is completely a cosmological constant model, almost identical to what we started out with, and subtract it from the data, you tell me if you see any trend in there. That is, the cosmological constant fits the data extraordinarily well. Now, people could say, well, what's your limits on W? Do we care? What does W mean? Tell me the theory that predicts W, and I'll tell you that that's an interesting thing to tell me. Other people can do this now. So here's the baryon acoustic oscillation measurements done in Australia, part of a 3-year program led by Chris Blake, where they have measured the BAO signal at a redshift of 0.6 from 240,000 galaxies. So here we have a completely independent way of measuring acceleration from the Sloan Digital Sky Survey and from the 2DF, the AA Omega survey with Wiggle Z. And you can see, again, the omega matter 0.27, cosmological constant 0.73, essentially identical model I just showed you on the previous diagram, and it fits the data perfectly. If you go through and want to do things like W, you can start adding constraints. Here's, for example, the BAO work. Here's work done by the Supernova Legacy Survey, combining omega matter and W with all the different constraints now from cosmic microwave background, baryon acoustic oscillations, and supernovae. And we keep on getting the same answer. Omega matter, everything's consistent with W. You could even now go through and simultaneously constrain the equation of state parameter, the amount of equation of state, stuff that's not, that has negative pressure, omega matter, and curvature simultaneously. And it, again, to very good precision, is consistent with the essential simplest model that we have at this point, a cosmological constant dominated model. The other thing is that the data on the supernovae are so good that if the universe is homogeneous and isotropic, the universe is accelerating. So what you do here is you give up, you take the Robertson-Walker metric, and you expand it as a Taylor series, where you, instead of putting in things from general relativity, you just put acceleration in it. And when you do that, you can go through and then go through and fit from the Robertson-Walker metric what the acceleration looks like as a function of time. And you can see the Q0 is about what we get now, of about minus 0.6, and it switches sign at roughly 0.6. But in this area, the universe is seen to be accelerating without the need to invoke general relativity. So, you ask the question, is there any way out of dark energy? Well, only if the universe is not homogeneous and isotropic. So I personally feel that Occam's razor does not favor us living in the center of a spherical underdensity whose size and radial fall-off is tuned to match the acceleration. There's reasonable constraints on that because we do look in different directions and we do measure very precisely now what the luminosity distance does back in time. There are those that disagree. I told this same thing to Joe Silk, and Joe Silk looked at me and said, well, I find having to make the cosmological constant 10 to the 120 orders of magnitude smaller than it naturally is even a greater fine-tuning. So it really depends on your perspective of what fine-tuning is. There is also a theoretical discussion, which I would say is controversial, but I think is hard, on whether or not the growth of structure can perturb the metric, the Robinson-Wachter metric, in such a way to mimic the effects of dark energy. This is the only way out I can see, but it's controversial. So the people who do this claim that as structure formed at a redshift of 1 or 2, that suddenly the basic tenet that we put on our model is no longer exactly valid. So I'm agnostic. It's hard calculation. Relativists get into fights when they talk about it. So my view is I'm happy to test it, but we need something observable. But I will note it has to somehow mimic the cosmological constant if this were to be right, to a very high degree. So what's dark energy? Well, one possibility is that the universe is full of a cosmological constant that is uniform in time and space. This, of course, was postulated by Einstein, but rejected by him later when it was realized that the universe was not static as he almost religiously believed up to 1929. Of course, if you go through from the particle physics side of things and ask, well, what's the natural size of a cosmological constant based on the number of virtual particle pairs in the universe, you get an answer which is 10 to the 120 or 10 to the 50, depending on where you cut your scale off, larger than what we measure. And that's a universe which we could never have existed in. So it's not really clear. Another idea is that it isn't the cosmological constant at all, that it is some sort of dynamical fluid not previously known to physics, but similar to what is postulated to have caused inflation. In this case, the equation of state of this fluid would likely not be constant, and it would vary with time. It would mean it would not exactly be -1. So the different theories of dark energy, which this is often referred to as, distinguish through their differing predictions for the evolution of the equation of state of the dark energy. Unfortunately, from my perspective as an observer, these theories offer at present infinite flexibility. They can predict any observable I can make. And so that means they're hard to disprove. So a long time ago, I was wandering around in Tokyo, and I had always thought that quintessence was invented, well, depending on your version, either in Germany or by Paul Steinhardt. But I realized it was actually invented in Japan by cosmetologists, where you see a hair and makeup gallery was there at the time. So finally, it could well be that general relativity is just wrong, as we've already discussed it. General relativity is well constrained, of course, from measurements, and there's not a lot of wiggle room for modifications to general relativity. But remember, if we modify general relativity, it has to mean that the natural theory just has things accelerating on its own with normal material in it. We can even start to test general relativity now. So things like the Wiggle-Z experiment and the BOSS experiment, which measure hundreds of thousands of galaxies, can go through and measure the rate that structure grows. And that is predicted by general relativity. And it is different for most modifications to gravity will provide slightly different view of this. And so if you go through and plot the growth factor of this stuff times sigma 8, from these experiments, you can see what the theory predicts for a cosmological constant universe and what the measurements are. And they're becoming interesting. I have seen theories that are sort of up here that were, I won't say particularly reasonable theories, but at least it shows that there is some ability here to start constraining the physics if people can actually write down a self-consistent gravitational model. So there are a lot of dark energy ideas out there, thousands at this point. They have lots, you've got to give them a good name. If you have a dark energy theory, give it a good name. But dark energy itself looks a lot like the cosmological constant. Indeed, we cannot discern it in any way from anything other than a cosmological constant at this point. And so we as observers are really searching blindly, hoping to find something that distinguishes our observations in our universe from one that contains a cosmological constant. The current currency that describes this is typically how well you can constrain the equation of state parameter, or if you really want to go, the first derivative of the equation of state parameter. I do want to remind people that this is a currency. It is really just parameterized ignorance. It is not telling you anything about any particular theory at this point directly. So our goal is to constrain physics based on models, not essentially what I would call meaningless numbers. That being said, you've got to have something to show whose is, my experiment's bigger than yours. And so that's the one we used. And so type 1a supernovae have lots and lots of experiments. As I said, I'm working on a nearby one to improve that here with the group here in Paris. We have things, for example, like the dark energy survey, eventually LSST, potentially Euclid will all do things. So they are currently the most precise measurements we have of the acceleration, but we are really getting close to approaching a systematic wall. We are limited by things of how accurate we can do photometry. We're limited about assumptions on dust. We're limited by how well we can constrain evolution. And those are becoming very, very hard. So I think it's a good thing to do in the short term, but 10 years from now, it's going to be very hard to make progress. The cosmic microwave background has had a renewed resurgence because although we've measured the CMB very well, Adam Rees has gone out and tried to improve measurements of the Hubble constant. It turns out if you can have a reason to believe you understand the Hubble constant absolutely accurately, then you can actually tie down the cosmology better with the CMB. So that is something that is going on. It's not clear how much more there will be done, but it's certainly interesting. I will also say that if you could go through and see polarization in the B modes, which that could really confirm or revolutionize the basic inflation CDM picture. That would be really interesting. May not explain what dark energy is, but it would certainly help solidify that side of things. Baryon acoustic oscillations, as I said, are really the simplest, most elegant, probably, solution. They are, mind-numbingly hard. Wiggle Z has put out its work. BOSS has shown a scale-free detection of the acoustic peak in their data with almost 500,000 galaxies. They should be able to get a very good measurement here in the next 6 months. They may well even be able to see the peak in the radial redshift direction, which allows you to measure the Hubble constant directly at that redshift. So BOSS is soon, and then we have potentially a 20 million galaxy survey with the Kip peak 4 meter called Big BOSS, which is proposed. Euclid, which of course you know very well here at IAP, which will be potentially doing the whole sky really as well as you can in about the next 10 years. You also have what I call measuring the growth of structure, and it turns out that is an incredibly accurate probe of dark energy if you don't have any systematic errors. So these methods have been, I would say, struggled to get rid of their systematic errors thus far. Nonetheless, if you use something like weak lensing, it is potentially a very powerful probe, the most powerful probe of dark energy, if you can limit your systematic errors. So Euclid will do a good job at trying to see where that happens. I personally think it's good they have the BAO experiment and the weak lensing experiment there, so that either way they'll get an interesting result. But it may just be that they will be very interesting for astrophysics on its own. We'll see. So in the end, my guess is the cosmological constant it's so close to the cosmological constant, it's not likely to be anything detected, but I don't know. The universe does what it does. But astronomy, because it really is still such an interesting field on its own, and people are doing all sorts of things, my guess is that as we explore the universe around us, and what happened over the last 13.7 billion years, where it might well gain insight into the cosmological constant or the dark acceleration in a way where we didn't expect. And so that is my best bet of how we learn about what's going on. And so that is where I'll end, and hopefully there will be some questions. Thank you.